We built a device capable of testing 10,000 PCBs a month, right in Dominic's bedroom. Well, not really. Turns out running an industrial testing line right next to a laundry bucket, it's a great way to get kicked out by your girlfriend. And frankly, I'm not keen on him sleeping on my couch after getting thrown out of his own apartment. So instead, we built it here, on the floor of our office, surrounded by empty shipping boxes.
But why do we actually need to build our own factory tooling? Why spend days of engineering a custom machine when we should be training AI models for dairy cows instead? Well, because of this. These are 120 freshly manufactured circuit boards for our next batch of cow tags. They just arrived from our contract manufacturer and right now they're entirely useless. Before we can seal them in a plastic housing and put them on an animal, every single one of these boards needs to be tested, supplied with power, flashed with the latest firmware and verified to ensure the sensors actually work. If we do this the manual way, plugging in fragile cables, probing tiny test points with a multimeter and waiting for the firmware script to run, it takes about 10 minutes per board, give or take. For this box alone, that is 20 solid hours of sitting on the floor doing repetitive manual labor, which is also prone to errors. And when we should scale to 1,000 boards or 10,000, no way. The math just doesn't work. So we needed to build a real factory-grade testing infrastructure, but we had to do it with 3D printers, cheap parts, and as always, basically zero budget. So first of all, how do the real factories avoid this doing by hand? Professionals use a process called in-circuit testing, usually built around a bed of nails test jig. Before we can seal one of these boards up and put them on a cow, we have to run it through a few basic steps. We check for electrical short circuits so we don't fry anything, we power it up and then flash the test firmware. The test firmware is designed to read data from all the sensors and the radio to make sure every single component is actually working as intended. Instead of plugging in tiny cables to do all that, you put a small copper pad on the back of your PCB called test pads. Then you build a mechanical clamp with spring-loaded pins that line up perfectly with those pads. You drop the board in, pull a lever, and all your connections are made instantly. And honestly, even if you aren't building thousands of boards, this trick is a game changer for DIY projects. Connectors are bulky and expensive. By using tiny test pads on the bottom instead of big plastic programming headers, you save tons of physical space on your board and you don't have to pay for the connector parts. You only need the connection while you're sitting at your desk flashing the code anyways. But if you order one of these custom jigs from a professional tooling company, it costs thousands of dollars and takes weeks to show up. Now to be fair, you can buy off-the-shelf manual test frames from sites like Alibaba. But while the bare mechanics might look cheap, the total price varies wildly. Plus you still have to get the pogo pin holding plates custom machined for your specific board layout anyway, and that's not an easy task if you don't have the 3D step files for that. Those Alibaba frames are a solid option once your production is more mature and you're ready to install a permanent tester straight at your contract manufacturer's facility. But doing it in-house gives us a lot more flexibility because we just need a basic test jig for the beginning. The strategy here is not to reinvent the wheel. We want to use as many ready-made off-the-shelf parts as possible and only custom design the specific pieces we absolutely have to. Step 1 was finding the actual mechanical frame as a starting ground. Like I said, we don't want to reinvent the wheel and we don't have time for that. When you're looking at test jigs, there are generally two ways they operate. One is a top-down approach, where the pogo pins are mounted on the top plate and moved down to poke the PCB. The other is a bottom-up approach, where the pins are fixed in the base and the jig's clamp pushes the board downwards onto them. So we hopped onto printables and actually found this really good and solid open source test jig design. Huge thanks to the creator for making this public. We've put a link down in the description if you want to print one yourself. We downloaded the files, fired up our Bamboo Lab printer, started printing and it failed. We hit a wall. Getting these specific parts to print reliably due to their size was a nightmare. But after tossing a few stringy failures and tweaking our settings, we finally got the skeleton built. We ordered the metal rods and springs online, put it all together, and honestly, the mechanical motion works flawlessly. It gives us this nice, smooth parallel clamping action to press down the board. but actually holding the pogo pins inside in place, that's a total nightmare. We don't just use bare pogo pins, we use these tiny metal press fin sleeves. They have a microscopic lip on them that needs to sit perfectly flush inside a recessed hole. Otherwise, the spring force of the pin just pushes the whole sleeve right out the back when you clamp down. If the 3D printed hole is even a fraction of a millimeter too big, the sleeve wobbles and our alignment is completely off. And 3D printed plastics, even on a highly tuned printer, just does not have that kind of sub-millimeter precision across a whole area of holes that we need. And to make things worse, if the test pad on the board you're testing are packed tightly together, you hit a physical limit on how close you can pack these pins next to each other while still keeping them accurate. We even looked into just ordering a bare circuit board and using the drilled holes to hold the pins. Turns out even standard PCB drill tolerances aren't tight enough for the kind of press fit alignment that we need here. So the 3D printed frame was fine for the structural stuff, but for the actual bed of nails we needed way more precision. And we obviously couldn't just mill a solid metal block or the whole thing would instantly short out. That's why the best solution is a CNC milled high precision polycarbonate adapter plate which holds the pogo pins in place. And this is where we have to be smart about where we spend our money, and the solution isn't to buy a $50,000 CNC machine, although that would be fun. The solution is to export your file in step format, go to jlccnc website, upload your part, complete the order, and around 2 weeks later this arrives. And honestly, unpacking this for the first time was so satisfying. It works beautifully. Dropping those receptacles into the machine polycarbonate and feeling them press fit perfectly flush with zero wobble.
Nice.
The rigidity of the machine plastic is on a completely different level compared to printed parts. We've been using jlccnc extensively for our projects in the last year, for example for custom aluminum parts for our pick and place machine, and they came out perfectly every time. So if you need any custom CNC parts, click on the link in the video description and we highly recommend using them. Then we just dropped the new plate into our 3D printed frame, secured it with a few screws, and suddenly our scrappy little clamp had a professional factory grade setup. We have the cheap printed shell for the macro movements and the precision non-conductive core for the micro alignments. With the plate populated, it was time to build the actual bed of nails. Pogo pins are essentially tiny spring-loaded needles. They are the holy grail of connector-less hardware testing because they let you make temporary, reliable electric connections by applying pressure. Press the board down, the springs compress, the pins hit the pads, and you have a circuit. Let go and it all disconnects. But since our CNC plate is just a solid chunk of non-conductive polycarbonate, those pins don't magically connect themselves to our testing equipment. We don't have a fancy custom PCB routing the signal for us, so we had to do it the hard way, fly wire soldering. Every single pin on this array needs a wire soldered to its back end to route the signal to our testing hardware. This is quiet, tedious, eye-straining work. You're holding your breath, trying not to bridge two microscopic pads with solder and carefully routing thin wires so they don't get crushed by the clamp mechanism later. It's not pretty. The back of this plate looks like a chaotic spiderweb of heat shrink and multicolored wires. But at the end of the day, electricity doesn't care if your wiring is ugly, as long as it's continuous and relatively short. The mechanical bed of nails was finally complete, but the mechanical clamp without a brain is useless. We need a way to actually automate the testing checklist, flashing and provisioning. We needed a way to automatically supply power, check for shorts, flash the firmware, and importantly, verify that the sensors are actually working and outputting plausible data. Building a custom testing circuit from scratch would have taken weeks. So we used Phidgets. These are these brilliant plug-and-play modular boards that let you read voltages, toggle power relays, and monitor digital inputs straight from your computer over USB. No custom circuit design required. And here is where our software stack gets a little bit unconventional. You'd probably expect us to use a Python script to run this whole show, since Python is the default for hardware scripting, but we actually wrote the main orchestration and the user interface in Golang. Why? Because testing the hardware is only half the battle. We also have to provision these boards. Every single tag needs to generate its own cryptographic keys and a certificate signing request before it can actually talk to our cloud. Doing this kind of crypto and spinning up a clean local web UI for the operator to monitor it is just way easier and more robust in Go than it is in Python. But Phidgets doesn't have great native support for Go. So we embrace the startup duct tape mentality. Our Go web server handles the UI, the crypto, and the overall testing logic. But whenever it needs to actually toggle the power, read a voltage, or pull the live sensor data from the board to make sure the accelerometer isn't dead on arrival, it just calls a tiny Python script under the hood. Go is the operator and Python is basically the worker talking to the hardware. It's a weird and slightly hacky architecture, but it gives us the best of both worlds and it completely automates the entire flashing, provisioning and testing sequence. Of course, provisioning isn't just about generating security keys and testing. During this exact same step, the Go server also writes specific metadata permanently into the board's memory. We log the exact hardware revision, the board type and the manufacturing date. This means we can maintain one single unified firmware across our entire fleet. When a tag boots up, the firmware simply checks its own hardware version and automatically adjusts how it interacts with the physical components. Plus, if a tag starts throwing weird errors out in a field 2 years from now, we have the exact manufacturing date on hand to track down batch issues. It adds maybe a second to the testing time on the jig, but it makes tracking field issues a whole lot easier. And here's the moment we've been building towards. Drop the board in, pull the clamp down and watch the UI do its thing. Power is applied, firmware is flashed, the sensors are verified and the crypto keys are generated. All in a matter of seconds. Instead of hunching down on the floor for 10 minutes per board, fighting with tiny cables, we are flying through this box. Slap, clamp, flash, done. We took that mountain of 120 boards and turned it into a neat stack of fully provisioned, verified hardware in a single afternoon. Out of this whole box of 120, we did find a few dead boards. But the beauty of this setup is that the UI immediately flagged them red. We just tossed them in the rework bin and kept moving. When we looked into it later, the accelerometer on those specific boards weren't responding to I2C commands. MEMS sensors like these are notoriously fragile. Because they have microscopic moving parts inside, they can easily get damaged by mechanical shock during overseas shipping or from thermal stress during the factory soldering process. If we didn't catch those dead sensors until the tags were already permanently glued shut or strapped to a cow, it would be an expensive nightmare. Catching them right here on the jig, that's just a mild inconvenience. Because we already verified every single component on the test jig, we know we aren't wasting time and material sealing a broken board into a waterproof case. We snap the boards into the plastic housings, apply the seal, and they are basically finished. We box the entire batch, update the inventory, and they are ready to ship out to the farm. And look, building your own test jig isn't just a fun weekend side project. When you are a bootstrapped hardware startup, building your own tooling is mandatory. You don't have tens of thousands of dollars to outsource this, and you definitely don't have the weeks to wait for it to show up while your production lines are sitting idle. You have to look at the problem, figure out where you can cheat with cheap plastics and where you need to pay for precision, and just couple the rest together with solder, Phidgets and weird mix of Python and Go. It's scrappy, it's a little ugly under the hood, but it works and it keeps the production running.
Now the batch is done, can we finally get rid of all this mess from our office?
Nope. Next batch arrives on Tuesday.